Okay, thanks for, I want to thank the organizers for inviting me and putting this conference together. It's been a lot of fun. And actually, you know, I might talk about quantum optimization and convex information if I get confused enough during this talk. So you never know. Okay, so what will I tell you about? I normally hate outlines, but I'm jumping around so much I think it would be helpful. I will begin by doing a bit of a review or introduction to quantum information. And I'll try and do it from maybe using the language that would be natural to people coming from an optimization perspective. So I'll try and express kind of the main ideas of quantum information in a way that hopefully will be useful. And I'm going to talk then generally about some of the optimization problems that come up in quantum mechanics. Kind of not necessarily the ones that I'm doing, but sort of the big ones in the field. And then I'll talk about how SDPs can be used for these. And then how we can analyze these LPs or SDPs using ideas from information theory or from quantum information theory. And this is sort of a coherent picture altogether which says that quantum mechanics gives us a new way of understanding tensors, and it gives us new metaphors and new language, and some of that includes ideas of quantum information theory. And so we can use ideas like conditional mutual information that are kind of have much more explanatory power than just sort of directly using linear algebra. And so I think that's a nice picture of using sophisticated ideas from quantum information theory to analyze these hierarchies. And then at the end, I'm going to undermine my message a little bit by giving you very simple algorithms based on epsilon nets that achieve the same performance as some of these. And this is very recent results that kind of I haven't fully digested, and I'm hoping maybe people at the conference can help me digest. Okay, so let me start off by just giving you a brief summary of some of the axioms of quantum information. You can think of it as a non-commutative generalization of probability theory. This is my non-commutative picture. So great. So what does that look like? So in probability theory, the states of the theory are vectors that have one norm equal to 1, and that are non-negative real numbers, called delta n, the simplex of these, the probability simplex. And what can we do with these states? One thing we can do is we can apply decision rules to them. So a decision rule might look like you get in a sample that's some number 1 through n, and then for each possible value of that, you decide either yes or no, again with some further probability. So if it's maybe you'll accept 3 always, and you'll accept 4 1/10 of the time, and you'll accept 5 never. And these numbers are just a bunch of numbers between 0 and 1, and you can call it a measurement. So if you get a sample, a measurement is something that turns that into a yes-no answer with some probability. So the chance of accepting, of saying yes, is just the inner product between these vectors. And so you can also think of it as the polar. So this is the L1 ball, or the positive part of it. This is the L infinity ball, or the positive part of it. And this is, so they naturally like to take inner products together. The L1 norm is sort of the natural one to use for states. For example, if you want to distinguish two states with the best possible distinguishing measurement, then the best bias possible is 1/2 of the L1 norm difference between these two states. Okay, so those are the axioms of probability theory. Quantum mechanics says that you do the same thing, but with matrices. And it happens to be complex matrices, but this isn't really a big deal. If it's just reals with negative numbers, you get pretty much the same phenomena. It's just mathematically a little nastier. So instead of probability distributions, we have what are called density matrices. They're also called states. And what these are n by n Hermitian matrices. They're positive semidefinite. That's analogous to the probability distributions being non-negative. And their trace is 1. And we can also call this the 1 norm, meaning the Schatten 1 norm, which is equivalent to the L1 norm of the singular values, also called the nuclear norm. Has a lot of names. So these are the basic states. Instead of vectors, they're matrices. And of course, their spectrum is a probability distribution, but then there's this additional degree of freedom, which is the eigenbasis. And if you've heard that in quantum computing, the basic states are complex unit vectors, that's in the setting where that's the special case of pure states, which are rank 1 density matrices. And that's when you know the state exactly. And this is sort of, you could think of it as a common generalization of probability theory and pure quantum mechanics. So it's when you don't know exactly what the quantum state is. Okay, so those are the basic states of the theory. What are the measurements? So by analogy, it's natural that these should be things with all their eigenvalues between 0 and 1. So it should be a positive semidefinite matrix because it should always produce a positive probability of accepting. And it should be upper bounded by identity because the probability of accepting should be never more than 1. And so you naturally get these constraints on the measurement operators. So Hermitian and all the eigenvalues are between 0 and 1. Again, the probability of accepting is given by this inner product. Again, the distance between states is sort of naturally done in the Schatten 1 norm. Okay, so these are the axioms of quantum mechanics, and they're basically just take the vectors and make them into matrices. Take the L1 norms and make them into Schatten 1 norms. Question?
How do you sort of interpret this distance between matrices?
The distance is the best bias possible for any measurement. So if I know that I'm given, let's say, quantum state rho with probability half and quantum state sigma with probability 1/2, and I get to devise whatever measurement I like, and I want to guess which one I have with the best probability of success, then the bias that I'm able to achieve towards the correct one is given by this quantity.
Because the infinity and the 1 norm are dual.
Yes. Right. It's basically the same argument as in the classical case.
Would you describe the total variation analog of?
That's right. You could also call it total variation distance. This is sometimes called the trace distance or the total variation distance. Same name is sometimes given. Okay. Good. So that's one system. Now you've mastered one quantum system. Now let's do two quantum systems or two probability distribution over two objects. So let's start with probability because it's more familiar. If you have two independent probability distributions, then the rule for combining them is called the tensor product. So let's say I have I roll one die and the distribution for the value of it is given by the distribution P, and then I roll another biased die and the distribution is given by Q. What is the joint distribution for the two dice? Well, the probability of getting outcomes ij is Pi times Qj. So the vector, let's say that each die has 6 sides, the total is 36. Then I have a 36-dimensional vector whose entries are given by these products. What is that vector? It's the tensor product. So the tensor product is just the vector you get by taking all possible products between the individual vectors. Now, I have this joint distribution. Suppose I want to just observe one of the two variables. So what do measurements look like? So suppose I have this joint distribution and I have some measurement, some decision rule about just the first variable or just the second variable. Then what the rule is that I tensor the measurement with a column of the all ones column. So it would say, I'm going to accept if I roll a 3 with the first die and I don't care what the second one is, I'll take the appropriate m for the first one and just tensor with all ones for the second position. Or if I want to make a decision rule based only on the second one, then I would do all ones tensor m. So this operation of taking m and tensoring on the all ones vector, you can think of that as a linear map. And its adjoint is the linear map that takes a joint distribution and goes to the marginals. So if I have the distribution of two objects and I want to get just the marginal distribution of one or the other, what I do is I sum over all the values the other one can take. So the marginal for the first position is given by summing over the second position, and the marginal for the second position is given by summing over the first one. Let me leave aside this last row for now. So what are the quantum analogs? Very similar. So if we have a product state, we have one quantum system prepared in one lab that has density matrix rho, another one in another lab with density matrix sigma, then the joint state is just a big density matrix, and here the rows are indexed by ij and the columns are indexed by kl, and you just take the matrix tensor product. So it's a big matrix whose entries are all the products of the individual matrices. Okay, just directly analogous. Measurements, similar story. If I want to measure just the first one, then I mathematically do that by taking the measurement operator for the first one tensored with identity for the second system, or vice versa if I want to measure just the second one. Again, this is a linear map. Again, The adjoint of it tells me the operation to get a marginal. So if I have a joint state and I want to figure out what is the marginal, then there's an operation that does this called partial trace. And what it looks like is I have this big n squared by n squared matrix. I want to extract the n by n state of the first system. So the ij entry of this is given by basically taking the trace over the second position. So the trace is you sum over the diagonal. And here you can see we're doing, it's like a trace just over the second position. This one is doing a trace just over the first position. So you can say that you're tracing out a system, and then what you're left with is the marginal state of what's left. It's directly analogous. One thing that's not analogous is what happens. So we know the product states are sort of a direct analogy. And now, what if you want to look at things that are convex combinations of product states? So mixtures of product states. For probability distributions, so the convex hull of P tensor Q. For probability distributions, this is everything. Every single probability distribution can be written as a mixture of some probability distribution on the first system, tensor distribution on the second system. You could just take them to be kind of singleton distributions. Another way of saying it is if I have some correlated information with Boaz, it could be that there's an external variable that completely describes our correlation. And if you knew that external, let's say Pablo knows that external variable, then conditioned on that, we could completely determine our respective states. And conditioned on that, we'd have no correlation. That's always possible with classical distributions, because Pablo could just know everything, right? He could just completely know our variables.
He doesn't.
But quantumly, Pablo cannot know everything. So quantumly, it's not possible. Another way of saying that is, if you take the convex, I'm sorry, this P here should be a rho. They look kind of similar. If you take the convex hull of all rho tensor sigma, meaning all convex combinations of state for the first system, tensor state for the second system, you do not get all possible density matrices. You get a set called the set of separable density matrices, meaning ones where all the correlations can be explained classically. And the things that are not separable are called entangled. And that's part of what makes quantum theory interesting, is that the existence of entangled states. If you didn't have these, then quantum theory might be a theory just of individual particles, but then sort of on a macro scale, things would just we'd be able to use classical information. But this talks about how information scales with the number of systems. And so it means it has fairly profound consequences. So the set of all n squared dimensional density matrices is bigger than the convex hull of products, which we call the separable states. And this, the things that are not separable we call entangled. So, okay, so that was a lot of definitions. Let me tell you now one of the problems that arises from this, one of the computational questions that we'd like to solve. It relates to an optimization problem related to entanglement. So one other definition of separable, I said you can decompose into density matrices. Of course, these density matrices you could further decompose into rank 1 objects. So you could always, any separable state, you could also say you can write it in this form. And this way is nice because these are the extreme points of the set of density matrices. So here, the PI is a probability distribution, and these V's and W's are unit vectors. So you could say that set is the convex hull of VV star tensor WW star. So you have this set, and one thing you'd like to do with it is, suppose you've prepared 2 ions in your lab. After painstaking effort, you've completely mapped out the density matrix that you've prepared, and then you'd like to publish your paper saying that you've created entanglement. Well, is the density matrix you've prepared actually entangled or not? So just the most basic question for a convex set is weak membership. Given a density matrix rho, and it's weak membership because I don't want to deal with right on the boundary. So I'll have the promise that either it's strictly inside the set or it's at least epsilon far away from the set in some norm. Determine which of these is the case. So this is sort of a basic computational problem that we might want to solve. And via kind of standard arguments, it's roughly equivalent. to an optimization problem, which is to optimize some linear function over this set. And linear functions on density matrices, it's nice to think of them as measurements, so though you don't have to. So let's say you have some measurement m, and you want to maximize the probability that this is accepted over all separable density matrices rho. And this function is called h sep of m, meaning h is like for the support function of the set S. Okay, so this is a basic computational problem. What can we say about its complexity? Is it sort of some obscure thing only interesting in some quantum experiments, or does it connect to other problems? And in fact, it turns out to connect to an enormous number of other problems. It's equivalent to many of the other problems, many of which you've heard about earlier this week. So it's equivalent to what I'm calling the injective tensor norm, also called the tensor spectral norm. Probably there are other names I'm forgetting, which is you have a tensor, and you want the maximum inner product over all unit vectors x, y, and z. Okay, it's like a tensor generalization of the spectral, of the largest singular value. It's also equivalent to computing the 2 to 4 norm of a matrix, meaning the largest 4 norm of the output divided by the 2 norm of the input. And you heard about this earlier in the week. It's equivalent to maximizing the 2 to operator norm. So instead of 2 to 4, it's 2, it maps vectors, and the input is in a 2 norm, to matrices, and then the norm of the output you measure in the operator norm of those matrices. It's equivalent to maximizing degree 4 polynomials over the unit sphere, and even to constant degree polynomials. And all these equivalences are, there's no dimension factors. If you have an epsilon error, it translates into an epsilon prime error in the other problem with no dimension factor. So they're really pretty sharp equivalences. There's even a relation to higher degree polynomials, but then it's sort of, the equivalence is not in both directions. Okay, so this is sort of the angle of this problem I want to focus on, but it's really the tip of an iceberg of a very large number of polynomial optimization problems. And part of why I'm focusing on it from this quantum perspective, apart from because that's how I learned about the problem, is that quantum gives you sort of a natural normalization to it, and sometimes you can say things naturally about it. But it's possible that for other problems, like small set expansion, there's a totally different normalization that's natural, and figuring that out may be part of how we make progress in this area. Okay, so it's equivalent to a bunch of things, but is it hard? Maybe these are all easy to solve. So what do we know about this? We know if you want to get a constant error, and now this is constant in the operator norm. So the operator norm might be much larger than h sep. So remember that h sep is the maximum trace of m times any separable row. The operator norm, if it's Hermitian and PSD, it's the largest eigenvalue. So that's the maximum of trace m row just for any density matrix row. So it's trivially greater than or equal to h sep. So this is kind of weaker than a multiplicative approximation. It's one of the weakest approximations I can think of for this. And even this fairly weak problem does not appear to be in polynomial time. It's at least as hard as planted-Clique, and at least as hard as solving a 3-set instance of length log squared n. So if you think 3-set takes exponential time, then you think it probably takes time n to the log n to solve this problem. So that's sort of the weakest version. What about multiplicative error? So if you could do a better approximation, and you need pretty weak multiplicative error. Like you don't even have to get plus or minus 1%. You could get it to within a factor of 100. And if you could do that, you could solve a small set expansion, which is an interesting problem. Connects to unique games, a lot of other optimization problems. So it would be very interesting if we could do this. And this gives us another route to it, to proving hardness or perhaps algorithms. And finally, what if you demand very high accuracy? So let's say you demand additive error of 1 over polynomial in n. And I put operator norm here, but I could have put h sep, because these differ by at most a polynomial in n factor. So this could have been, I could have said this was multiplicative error. Not sure why I didn't. If you do this, I remember why I didn't. If you do this, then this is at least as hard as 3-set. And now your input is size n, so this is, it's as hard as a 3-set problem of roughly the same size. And this is originally due to Gurvitz, and the best dimension in this polynomial is due to Legal, Nakagawa, and Nishimura, and they got this to be basically n polylog n, this thing in the denominator. So, which there's some evidence that might be sharp as well. So this is sort of the range of hardness. If you want to get it to constant error.
Aaron, you mean for the operator norm? For the operator norm, the thing in the denominator is like n.
That's right. That's right. That's why I didn't make it multiplicative there, because I didn't know how to report the result for multiplicative. Good. Okay, so that's what we know about hardness, and so kind of one. I'm not going to really get into the techniques involved here because they take us a lot of different directions. I will say that one nice thing that you get out of this, and it's sort of a common question is, when do we need quantum techniques to analyze things that are not apparently quantum? And maybe you don't need them, but it's sort of helpful to look at it that way. So one thing that from these results we know how to prove, and I do not know a nice way of explaining it that does not involve some quantum-ish things, is this 2 to 4 norm, which is sort of closely related, but not quite equivalent to smallest set expansion. We know it's quasi-polynomial hard, so this n to the log n hard, to approximate the 2 to 4 norm. And that's something which is came from using quantum techniques, and still, I don't know a simple way of explaining it that doesn't involve something quantum. But I think that's maybe a question, because to simplify the proof in any case. Okay, so this is kind of one problem, which is a basic optimization problem that comes from quantum information. And I want to switch gears and tell you about a different problem. And to do that, first I'll give you kind of more of the basics of quantum information. So I told you about one quantum state, and I told you about two. Now what about n quantum states? And I'm sort of changing the terminology a little bit. Each individual system will now have d dimensions. Think of d as small, like 2. And there's n of them. So it could...
So there is a typo here.
Yes. That should be n d-dimensional systems. Thanks. N d-dimensional systems have d to the n dimensions. And the fact that the number of dimensions grows exponentially with the number of systems is a basic and interesting feature of quantum mechanics. It explains the power of quantum computers, why they cannot be... There's no obvious way to simulate them classically. There might be a very non-obvious way, but if you try to just write down the state of a quantum computer, it's very hard. And it also explains the difficulty of classically simulating quantum mechanics. If I have n atoms and I want to simulate their joint state, the naive simulation takes effort exponential in n. And it was, in fact, this realization that led Feynman to propose using a quantum computer to perform the simulation instead. And then, kind of once you've accepted that quantum computers might do better on one problem, simulating quantum mechanics, then it's sort of more plausible to believe they could do better on other problems as well.
Can I just add that, the dice example, if I have n dice, also has exponential dimension in your formulation. But it's the separability that lets you, simulate things classically. I think people sort of gloss over this.
Right. So you can also get an exponential speedup by going to randomized things. So if you have a randomized algorithm...
It's not known how to simulate a separable quantum computer, right?
That's a complicated question. If all of the dynamics are separability preserving, then yes.
Okay.
But you could have it's not known if you just are simply given the promise that your quantum state is always separable, then it's not known how to simulate it.
I see. But if the gates are always preserving separability, then you can simulate it.
And if you start with a separate product state, yeah.
Okay.
There's also some results that relate, like the amount of entanglement. Like if I cut somewhere in my circuit and I look how many qubits are entangled, then there's some relation between this number of qubits and the simulability.
Yeah, if there's low entanglement, then we can simulate it. No, it's true though that this is sort of an exponential speedup, but it's reminiscent of the earlier exponential speedup that we found when we went from deterministic to randomized. Because with a Markov chain, you've got a little random index pointing into a giant space, and you're effectively manipulating these exponential-sized probability vectors, but you're not storing the whole probability vector, you're just storing a sample. So it's reminiscent of that. But the things you can do with a quantum superposition are more interesting than the things you can do with a random sample. So I'm not going to talk too much about algorithms, but more about the optimization problems that come with it. I'll mention there's another way of thinking about these multipartite states that maybe connects it to other things that you might be more familiar with. So the density matrix here has 2n indices. It has n row indices, each one going from 1 through d, and n column indices, each going from 1 through d. So you can think of this as a 2n index tensor, of which n of them are labeled as row indices, and n of them are labeled as column indices. So here I've taken the example of n equals 3, and this is what row might look like. And then many operations that you want to do, you can interpret as gluing these tensors together. So for example, the partial trace is you set I3 equal to J3 and you sum over all those values. And that just means basically drawing a line between them. Whenever you when you draw a line, then you sum over all the values of that index. And if you want to perform a measurement, then you multiply the two, which means stick the two next to each other, and then take the trace over the whole thing. And these pictures are nice. For example, it's transparent from here that trace m row is equal to trace of row m. And there are a lot of other things you can do with these tensors.
Is there a natural thing of multiplying two states? Is there some natural interpretation of that?
There is. So there's one thing you can do if you're given. Let's talk probability distributions. So if I'm given a sample from P and a sample from Q, I can ask, are they equal to each other? And the probability that they are will be the inner product of P and Q. Similarly, if I'm given two quantum states, there's something I can do called a swap test. And the probability of it accepting will be not quite, but close to trace rho times sigma. So there's an operational thing you can do that will produce that. Yeah. And actually, that swap test is used in some of those hardness results, like the 2 to 4 and all thing. Okay, so good. So what do we do with these big tensors? I've talked about states. What about measurements? So one thing we can do is we can measure a subset of the positions. And I want to talk about something that's related to physically you wouldn't call it a measurement, you'd call it an observable, which is specifically something called a Hamiltonian, which is a way of describing the energy of a system. In general, if I have n particles, let's say I have n electrons, the energy of this collection of n electrons will be the sum of all the pairwise contributions. So electrons interact 2 at a time, and the energy is related to the distance between these two electrons. And so to get the energy for all n, it's not an arbitrarily complicated function. It's just a sum of all of the pairwise properties of some function over all. I sum over all pairs of electrons and evaluate some function of their individual properties. And so the way to express this in matrix form is it as a k-local operator. So remember that if you want to ignore a position, you want to measure one thing and ignore another position, you put an identity in all the positions that you want to ignore. And so if you have n positions and you want to ignore all but k of them, you put identity in all but k positions. And the resulting matrices are called k-local. Or really any linear combination of things like this are called k-local. And one way to get intuition for what these means is think about the case when it's diagonal and you're sort of back in the classical setting. And this is like looking at a k-constraint satisfaction problem. So how many things are satisfied in a k-CSP? Well, it's some function of subsets of at most k variables. In the Boolean case, this is like degree k polynomials over the hypercube. So in the diagonal case, it's something that you should be familiar with. And this is sort of the natural matrix generalization of that. And they're also physically relevant because the energy of physical systems is always expressed in this form. Specifically, if there's some h and the energy is of the form trace h times rho. So this raises the local Hamiltonian problem. So given some h, which is k-local, and even though it's a giant matrix, because there's not that many k local operators, this is a small dimensional vector space, you can give a succinct description of H. So this is, you can write down a short description of H. The local Hamiltonian problem asks to find the smallest eigenvalue of H. I guess in optimization, you often want to find the largest eigenvalue, but here you want to find the lowest one. It's basically the same problem, but that's because physical states, when they're very cold, like to be in their lowest possible energy configuration. But basically, it's just find the smallest eigenvalue of this giant implicitly specified matrix. Okay, so what can we say about this problem? Well, we know from the diagonal case that it at least includes NP, because it's like max CSP. And in fact, it's a little bit harder than NP. It's something called quantum Merlin-Arthur, if you want to get this 1/poly accuracy. And this corresponds to something that a quantum polytime circuit can verify if given a quantum witness, I mean a witness that's a quantum state. Classically, we know a PCP theorem which says that even to get this to sort of constant error is still NP hard. Quantumly, we know that it's NP hard, but we don't know that it's QMA hard. And there's something called the quantum PCP conjecture, which says that this is QMA hard, which I'm not going to go further into, but I just want to tell you kind of the range of knowledge on this subject. You might ask sort of who would care, QMA versus NP? Both sound really hard to me. And one way I like to think about it is, what would it mean if the local Hamiltonian problem was not in NP, but it was in QMA? Then that would mean you have a Hamiltonian, you can succinctly describe it, but then to show that the lowest energy state is below some value, you cannot explain that with a classical witness. The only way to demonstrate that the energy is below some threshold is to physically give the quantum state. So it's like we finally make contact with aliens. The first question we ask them is, look, I can't solve the Hamiltonian problem of the proton. Can you tell me how to solve the quantum chromodynamics here? And they say, yes, I have a proof that the ground state energy of this is such and such, and the proof is, here's a proton in the ground state. Measure it. And, that's not very insightful. As a theoretical physicist, your goal is to give a theory that you can publish in a journal, hopefully. They'll be classical and copied many times. And yes, NP complete things are maybe very hard to do, but you are very overconfident, so you believe you can guess the witness. But if it doesn't even exist, then there's no way to do that. So that's why people might care about this. And people talk about this stuff often kind of abstractly, and they say like, this is like a quantum generalization of constraint satisfaction. I want to kind of emphasize that this is really like solving practical examples of this is actually something that's very important. So let me just give you a very concrete example, something called the kagome antiferromagnet. So there's this mineral called Herbert Smithite. I'll give you one guess as to who discovered it. It has these sort of well-separated planes, and in each plane, if you were to take an electron microscope, you would see some image like this. But this is actually just a blurry picture of a wicker basket. But it has similar structure. And you can see it's sort of... it's good for Rosh Hashanah, actually. It's sort of this pentagon, this hexagon kind of pattern. And there's a spin at every site, and they're antiferromagnetic, which means that spins next to each other want to be anti-aligned. And there's this belief that this is something called a quantum spin liquid, which means it's neither ferromagnetic nor para or diamagnetic, but it's this other phase, which has this topological order, something that would be very interesting if we could understand it better. Experiments are suggestive, but we know exactly the Hamiltonian, but we're just not smart enough to solve it. So we cannot write down an exact solution. So what can you do? One thing you can do is numerics. So here's a paper that was there was a big splash. It was published in Science a few years ago by some major people. And I don't know if you can read this, but we simulated this model numerically on cylinders with circumferences up to 12 lattice spacings, right? And this was huge. Like to be able to do this on something of circumference 12 was like a great numerical result, and something that people were very interested in, and and being able to push this further and to improve the quality of the evidence would be like really a great thing. So even though asymptotically these things are exponential, if you can kind of fight the exponential in any way, then that can be of tremendous interest. Okay, so that's kind of an example of one of the things you'd want to solve here. There are many other examples from chemistry. And let me come back to theory land and talk about another way of viewing the problem. So I changed it from K local to L local. So suppose you have an L local Hamiltonian and you want to find the lowest energy. Then there's another way of thinking about it. You can write H as a sum over these local terms. So H sub S is some subset of size L. H sub S acts only on that subset. And that means that when you take trace of rho times H sub S, that won't depend on all of rho. That just depends on the marginal of rho on those particular sites. So let's call that marginal rho superscript S. So the energy of the system is this sum of the energies of each little marginal of rho with the appropriate Hamiltonian. And so this is nice because here the basic operators are huge. They're d to the n dimensional. And here the basic operators are not so big. Think of L as like 2. Then these would just be d squared dimensional matrices. Maybe d is 2 also, so then they're just 4 by 4. So it's really a much, much easier problem, or at least the objects involved are much smaller. So this suggests there's going to be a lot of d and n. This should be d to the L dimensional, this should be d to the L dimensional convex optimization. Oh, no. I take that back. N to the L is right. It's like n, because there are n choose L different sites. I psyched myself out. So this suggests a convex optimization of much smaller dimensions. So before I said there's an exponentially large matrix, find the smallest eigenvalue. Now there's a bunch of small matrices. There's n choose L matrices, each of dimension d to the L. And what you want to do is optimize this linear function over them. But the catch is that the constraint is killer. The constraint is that these local density matrices have to be globally compatible. There has to be an extension of them to a global density matrix. And already for probability distributions, this is hard, right? You can do the same thing for probability distributions, and if you could solve this quickly, you could solve NP-complete problems. And the catch there is that the probability compatibility problem is hard. And same thing here. This is QMA complete to check. So it's not, it's not a get-rich-quick scheme, but it does suggest a method of approximating it. So here's a relaxation. So you optimize the same linear function, but now take a larger set of variables. Take your variables to be all subsets of at most k systems, where k is something larger than L. And demand that these, when they overlap, be locally compatible. And this gives you as you increase k, you get a more and more accurate approximation. When k is n, you're solving it exactly. And this gives you a hierarchy of semidefinite programs for solving this problem. I'll come back to this soon, and we'll talk about a slightly more sophisticated version of this. But I want to mention for now this other perspective on the problem. So I'm going to return to local Hamiltonians. I first want to mention, just to kind of give you an overview of the field, a few other variants of this problem that are also interesting. So one of them, sorry the color came out funny, is to find not just the ground state energy, because that might be just some number, what do you learn just from one number. What you really want to know are properties of the ground state. So for example, in the kagome antiferromagnet, the question is whether it's a quantum spin liquid, which relates to correlation functions between spins that are far away. You want to know how does a correlation function behave with distance. This is a local observable. And so what you want to do is, given the ground state, estimate some local trace of some local observable with it. And that is nice because you can reduce it to the same basic minimization problem. Another problem, which is somewhat harder, is to estimate the partition function. So the partition function of a quantum state is trace of e to the minus h divided by temperature, which I left off because it's just a constant. And then sometimes you can take the log of it, you get the free energy, you take the derivative of that, you get all kinds of other thermodynamic quantities. And this is another important thing that you'd like to estimate. And here the complexity is somewhat different. It's often it's pp complete to get it. Sorry, I don't know how I said that. It's sharp p complete to do it exactly. But there are some special cases that can be sometimes much easier. Like valence match gates are an example where you can do things much better. Finally, another thing you can do with these big Hamiltonians, e to the minus h corresponds to thermal states, non-zero temperature. E to the I times h corresponds to time evolution. So if you want to simulate what a quantum computer does, it boils down to estimating matrix elements of this operator. And it's BQP complete to do this, which means it's as hard as doing a polytime quantum circuit. So these are kind of all different things that you'd like to do with Hamiltonians. And there's a lot of room for approximations of these different problems. So I just want to put them out there as things that would be very interesting to make progress on using convex optimization. Okay, so I've mostly talked about problems. Let me talk about solutions, about how we can solve them using things like the sum of squares hierarchies that you've heard about before. And first, I'll give you a little overview and then maybe go into a little more detail. So one thing we'd like to do is approximate the set of separable states. And there's a relaxation called K extendable plus PPT. PPT means positive partial transpose. And I'll say a little bit more about this in a minute. So that's the first problem I mentioned was separability testing, and there's an SOS hierarchy for this. Another problem is the ground state energy, this lowest eigenvalue. And here there's a different different relaxation, which I'll also give you more details about in a minute, which appears to be incomparable. It seems like maybe they should be related, but I don't see any direct relation. There's a third one, and I think I'm going slower than I thought, so I won't go into detail, but I want to say that the talk right after lunch by Miguel Navasquez will go into more detail about this one. And this last type of hierarchy is also related to quantum problems, something called quantum games, which are related to interactive proofs. And it involves not the normal positive Stellensatz used for the SOS hierarchy, but something called the noncommutative positive Stellensatz, which is something I understand much less well, and it's harder to prove things about it, like it's convergent.
And the first two relaxations, they are not special cases of like the sum of squares for like. They are.
But what I don't know is, if you have a proof that this one converges, does that give you a nice proof that this one does, or vice versa? They feel sort of
different problems, right?
Yeah. So let me say a little bit more about this first one in a little more detail. So instead of talking about SEP, let me talk about something called SEP sim R for real. So let me take convex combinations. I'm going to take just real vectors, XX transpose tensor XX transpose. So if this were SEP, this would be like VV star tensor WW star. But this is a restriction, but it's pretty minor. You can show that computationally this is just as hard. But it makes the math simpler to write down. So you can think of this is like degree 4. This is like all the degree 4 monomials. And the natural SOS relaxation is to consider all the degree K monomials and to give some opinion about what all of their expectations should be. These are the pseudo expectations that you heard about from, I guess, John and maybe David and maybe other people too. So the way it works is you take sigma to be a density matrix of dimension n to the k, so you can think of it as having k systems, each n-dimensional. And you demand that it be fully symmetric, so there's 2n indices. And if you permute, 2k indices, and if you permute them in any way, you get back the same thing. And then if you trace out all but 2 systems, what you're left with is your approximation here. So what do I mean by fully symmetric? I mean, let's say here are your tensor indices. So if there's any way you can think of twisting these around, as long as you still have kind of 3 lines coming in here and then 3 lines coming out there, it should give you back the same tensor. In particular, you can rewire it in ways that does not respect the matrix structure. You can mix rows and columns. That's what this partial transpose means, is to mix the rows and columns just of one position. So this was introduced by Pablo and his co-authors over 10 years ago, and they show that it converges and some other properties of it. There's other versions that use less symmetry as well. So if you want to attack actually the separable problem, not this sort of toy version here, you do something called k-extendable and PPT. The details are not that interesting about the difference, but I just want to say that when you hear about k-extendable and PPT, you should think about this toy problem, and that sort of reflects what's going on. So this is a hierarchy that often performs pretty well, and in a minute I'll tell you more about what we know about its performance. We also have hierarchies for the lowest eigenvalue. So I presented one, which is to look at all the marginal states and to demand that they be compatible. But if you use sum of squares, you can it suggests actually something a little bit stronger. So let me just recall the exact problem. So the exact problem is that you want these these things called reduced density matrices to be compatible, meaning that there is an extension to a global density matrix. That's hard. Let me give an equivalent formulation, still hard. So define some map L, which is meant to be, and L is a map from k local operators to real numbers. So whenever you're given a k local operator, L will tell you its opinion about trace of that operator times rho. And you say that L is valid if it corresponds to an actual state. So for any operator x that's k local, L of x should be equal to trace of rho times x. So obviously that's hard to check. So it's just an equivalent way of saying this problem up here. And now we can do a relaxation. We can say, well, let's just demand that L satisfy as many properties that we can test with a small SDP. So again, we minimize the sum of L of all the local terms in the Hamiltonian. And now what do we know about L? If it came from a valid state, certainly normalization is that L of identity should equal 1. That part's easy. But also, it should have this PSD condition. So if x is k over 2 local, then x star x is k local. And so it's something that we have an opinion about. We can say what L of x star x is. And this is a PSD operator. X star x is PSD. So L of this should always be greater than or equal to 0. So if L is valid, this will certainly be true. Of course, it's not the only condition. Until you take k to be like n, you won't get this to. This won't be a perfect test. But it'll be some test. It'll be a relaxation, and you can check it efficiently using semi-definite programming. It's basically a straightforward application of the sum of squares method. So with sum of squares, we have these two natural hierarchies, and I think it's a great problem to try to better understand how well they perform. And we know a little bit about how well these perform, not as much as we could. The bounds we have are nowhere near the matching results from complexity theory. And so I think that one of the main open problems here is to try to improve that in either direction. So I have maybe 10-ish, a little less than that, minutes left. Let me try and quickly tell you some non-trivial things about bounding the convergence of these things. So to do that, so let me just say there's been a lot of work on showing that these things do well using quantum information theory. And using things like quantum conditional mutual information, and a lot of really wonderful techniques that I love, that I will not have time to tell you about. But I can tell you about a classical analog that is hopefully more comprehensible and that expresses many of the key ideas. So let me tell you now a classical analog. And if you were completely confused before, that's okay, because it's sort of a fresh start. Let's consider the problem of quadratic optimization over the simplex. You want to maximize Q as some input, You want to maximize the inner product of Q with P tensor P, where P is a probability distribution. This is equivalent to looking at the convex hull of all the P tensor P's, which is a convex set, obviously, and computing the support function of that. Now, even though it's a convex set, it's not easy to do this optimization because we don't know how to test membership efficiently in the set. So this will be a hard problem. In fact, if you take Q to be the adjacency matrix of some undirected graph, then this maximum is exactly equal to 1 minus 1 over the clique number, which is kind of a cool result. Usually these things are not, you don't have any sharp equality like that, but here you do, and that gives you really a sense of how hard this thing is to compute. Okay, so what's the relaxation? There's a relaxation which is a close variant of sum of squares. It's basically sum of squares light, kind of throwing away some of the constraints. The relaxation will be to take Q to be a symmetric probability distribution, also called an exchangeable distribution. So it's a distribution over k objects, each with an alphabet of size n, and it's symmetric, meaning if you permute these objects, you get back the same distribution. We'll call that an extension of the distribution, and then we'll take pi, which we hope is close to P tensor P, we'll take pi to be the marginal on the first two positions of this distribution. Okay, so we take this symmetric extension, and then we look at the first two, we take this symmetric distribution, and we look at the first two positions of it. Okay, so why is this a good distribution? The idea is, you can think of it like, well, yeah, I'll say that in a minute. So why is this good? This was proved actually almost 35 years ago that this works well, and then Pablo and his co-authors gave a totally different perspective on this with some, in some ways, stronger results. And these showed that the distance of what you get, of pi, to the convex hull of P tensor P goes like 1 over k. So that means if you want to get error and this distance is in the variational distance. So that means if you want to get error that goes like the largest entry of Q divided by k, the runtime is n to the order k. And why is this something we should expect? One way to think about this is if Q is symmetric, that means it's a combination of different types. A type just means there's this many 1s, this many 2s, this many 3s, etc. And it's just, you fix some type and you put them in all different orders. And then the difference between pi and what it should be, it's like the difference between drawing 2 samples with replacement and 2 samples without replacement. And you can show that if you're drawing these from an urn of size k, then as k gets large, these two distributions get very close. That's basically the analysis of Diaconis and Friedman. And what Pablo and his co-authors did was like a sharper, like looking at all the extreme points and doing some more exact things. So what's happened here? We took a sum of squares hierarchy, and we used reasoning about probability theory in order to show that it converges. And there's another example of this, which is a little bit more sophisticated, but I'm really running short on time. So let me just say it very quickly. So it's an algorithm for Nash equilibria, which I just maybe won't define if you don't know what it is already. And a relaxation of Nash equilibria is a correlated equilibrium, which satisfies all the same linear constraints. And Nash equilibrium is a correlated equilibrium that's a product distribution. So correlated equilibria of an LP4. So what you want to find Nash is an LP with this product constraint, which is nonlinear. So the complexity is sort of quasi-polynomial, but I will not get into that. And what I want to present is that you can, and previously there's an algorithm which is also quasi-polynomial that involves enumerating over epsilon nets. What I want to present is one using, again, a sum of squares-like algorithm. And the idea is the following. You search over distributions over k plus 1 players. There's 1 Alice and k Bobs. And it has the linear constraints are that every marginal of Alice and one of the Bobs should be correlated equilibrium conditioned on any possible values for the previous Bobs. So the size of this is like n to the k, and the number of constraints is also on that order. So it's a linear program running in this time. And what I like about this is that there's this slick information theory analysis, which really fits right here. So what do we have to show? So we know that we're getting correlated equilibria. We can just show is that they're nearly product. How do you show that something is, when you have two variables conditioned on a third, how do you show that they're conditionally nearly a product? That's like saying that their conditional mutual information is very small. And if you use the chain rule of conditional mutual information, then you can show this pretty directly. So it's a trick I learned from Prasad, and I've used it like, if I didn't know about this trick, I wouldn't have had any research output, I think, over the last 5 years. Used it a lot. So entropy of A is at most log m, because that's the support of A, which is upper bound for the mutual information, which you can write as this telescoping sum of mutual information of A with B1 plus mutual information of A with B2 conditioned on B1 plus ... mutual information of A with BK conditioned on everything that came before. So there's k terms here. They add up to log m. So one of them's got to be small. So there's some I such that the conditional mutual information is less than log m over k. And if you take k to be this number, then you get that the conditional mutual information is small. And that means that the things are conditionally almost independent. Which means that this hierarchy does a good job. So I find that really cool, that these hierarchies, which really feel like they're about linear algebra and polynomials and algebraic geometry, here's this like thing from information theory that can help analyze them. And for the quantum hierarchies, there's a really analogous explanation for why they converge, which is really not much more work. And I don't have time to present it, but it's if you understand this, then it's not much more to understand the quantum ones. And what the quantum ones say is you get some bounds, which maybe you can ask me about later if you want, because I don't want to eat into your lunch. And in one case, they're not sharp, but they're almost. And then the other case, we actually do precisely match a hardness result. So we know that for the case of many parties, and it is sharp. We also, building on a result of actually 3 people in the audience, can show that this SOS for the smallest eigenvalue for the ground state energy, that here we can show that this hierarchy does a good job for graphs with low threshold rank, meaning that they have a small number of large eigenvalues. And I kind of just want to tell you that these results exist, because I don't have time to tell you why they work, except to say that they're based on information theoretic type ideas.
Sorry, just one question.
Yeah.
So these ones for lambda min, the relaxation that you're using doesn't use PPT, right?
That's right. That's right. And also these results for HSEP, they don't use PPT. We in general don't really know how to make good use of it. There's some evidence that it may be very helpful. Okay, so maybe I'll just skip over the fact that you can do these things with epsilon nets. I will say that this is like most of the proof, so it's pretty concise also. You can generalize it to factorization norms. I'll skip that too. I'll briefly mention that there are many problems. So this maximizing quadratic function of the simplex, approximate Nash, HSEP, something else called free games, which is like you have 2 provers, but you ask them uncorrelated questions. For all these problems, we now have basically identical performance between the best epsilon net algorithm and the best sum of squares algorithm that we analyze using information theory. In only this case, the paper by Pablo and his co-authors, is there like an explicit correspondence between these 2 methods. Otherwise, it's just sort of this suspicious coincidence that they yield the same thing. So that's something I would really like to understand better, is if there's some more general reason why we should expect these things to yield the same results. And I apologize for the fact that I didn't tell you anything about the epsilon nets. So from my talk, you would have no way of guessing how this column goes. But ask me about it later, and I can tell you in person. It won't take long. Yeah, so let me conclude by saying that there are a lot of open questions. So we have some hardness for the 2 to 4 norm, quasi-polynomial hardness. And we don't quite get quasi-polynomial hardness for small set expansion. but it feels in some ways like we're close, and it'd be very nice to be able to get that. In general, we have some quasi-polynomial algorithms and some quasi-polynomial hardness. Sometimes they match, sometimes they don't, and getting them to match in more cases would be really cool. Dynamics, I think, is another place where these hierarchies could be used. If you want to have, Stephanie mentioned that if there's always low entanglement, then you can get a good simulation. But what if there's a noisy circuit with some version of low entanglement? Can you sort of make use of the noise? Like, for example, if you want to simulate the D-wave machine, can you do that with a few number of rounds of the hierarchy? In general, we'd like to know more conditions under which it's easy to simulate, for example, find the ground state of Hamiltonians, relate hierarchies and nets I just mentioned. And finally, for the information theoretical analysis of Nash equilibria, we use the classical conditional mutual information. Quantumly, it's been hard to make progress because it's so hard to talk about the quantum conditional mutual information. It's in many ways a more mysterious beast. And so I think this is also something worthy of direct study. Here are the papers that I've worked on, which involve this stuff. And I want to thank you for your attention and tell you it's time for lunch.
Can you go back to the slide on epsilon nets?
This one.
Yeah. Freaking. Yeah. Is your construction in the quantum case similar to the? So the top first three, the constructions are all through Moiray's empirical method, right? Where you basically you're on the simplex and then you generate it. You show that the size of the epsilon net scales the way you'd like it to.
Yeah, you're saying all the epsilon nets use empirical method.
Yeah. Does the one for HSEP also use an empirical method, or is it a different construction?
No, it also uses empirical method.
So in some sense that is information theoretic, right? I mean, you're...
Yeah, because you could say for the epsilon net, it's like you need k samples, and then for this one you need k rounds, and so maybe these extra rounds are behaving like more samples.
I don't know, but I was just going to throw that out.
Yeah, that seems plausible.
It's always the case that if you have an epsilon net algorithm, that it implies that that's SOS also goes, right?
Oh, I didn't know that.
Always the case?
How do you know that it's an epsilon net?
I mean, if
how do you prove that epsilon net is actually not?
I don't know if you need to. Yeah, I'm not sure. Okay.
That's a great question, and we can talk later. I can tell you examples where I know how to get a better bound with the epsilon net than I know how to get with the hierarchy.
Oh, okay.
So then, being able to achieve that with the hierarchy would be really cool.
Okay. Just want to say what I mean. Not I guess in those cases, are the epsilon nets generated by that in this randomized way, or in those cases the epsilon nets are?
Yeah, they are. It's just like you use like a better Chernoff bound.
Gotcha.
Like taking more advantage of the structure. So maybe the hierarchy also works better, but you have to improve the analysis. And since our methods of analysis really do look different, then I don't see how to improve the analysis the same way.
Sorry, but I'm confused. I mean, somehow at least in the simplex case, you have an explicit epsilon net. So in these cases,
in all of these cases,
randomly.
The what?
If you generate your epsilon net randomly, then you're actually proving this. I mean, it's not.
No, in none of these, we're not generating the epsilon nets randomly.
Oh, I see.
No.
That's
the constructions in existence are it's just using the randomized method.
Yeah. The constructions will look like this. They'll say, look, if I have an average of a bunch of matrices and I sample k of them, then with probability greater than 0, I'm close to the mean. Therefore, there exists a sparse combination of them which is close to the mean. So if I enumerate over all sparse combinations, I'm going to find it. So they typically take this, have this form.
Okay.